We're going to start looking at 1.31. And where it says to give the formal charge if one exists on each atom of the following molecules. Define for me formal charge. What does it mean?
The overall charge on the atom.
It is a charge on an atom, but how do we figure out what it is? Okay, what electrons? All electrons? We're only talking about valence electrons, right? So we need to go through and figure out how many valence electrons each atom formally owns, correct?
Correct.
So I'm going to expand this out a little bit so that I can see everything a little more clearly. Am I going to have a formal charge on any of the hydrogen atoms?
No.
Why not?
Because you only have two valence electrons.
They have two valence electrons, right?
So they can't form one. And they don't have any more.
Okay, so there's two valence electrons in the bond, right? But how many does hydrogen formally come in with?
One.
One. And how many does it own from the bond?
One.
One, right? So we don't have to worry about the hydrogens. How about the carbon?
It's good too.
It's 0, right? It comes in with 4, it formally owns 4. How about this oxygen?
It's fine. It's good.
It's good. How about this one?
It's good.
How about this one?
It's good.
How about this one?
It has a negative charge.
Okay, how do we know it has a negative charge?
Because it came in with 6 and now on 7.
That's right, it owns 7, right? So if we look at it, and we circle it, it owns all 6 of the lone pair electrons, and it owns 1 from the bond, right? 6 minus 7 is always minus 1. That's what I always like about organic chemistry. The math is that simple, okay? I don't have to worry about anything else. How about for sulfur? How many does it come in with?
6.
6, and it owns 6, so it is overall 0, right, or neutral. Absolutely. All right, let's look at another one. Let's look at all right, walk me through it. What about the hydrogens?
They're all zero.
They're all 0. How about the carbons? They're all 0, right? How about the oxygen? -1. Do we really need to calculate that one? No, we know that oxygen that has 6 valent or 6 lone pairs around it and a single bond is going to be negatively charged, right? And that's like hydroxide, for example, right? So that's pretty common. How about the sulfur? Right, so we circle it, it comes in with 6, and it owns how many? That's right. And so the overall the molecule is neutral, but oxygen bears a negative charge, sulfur bears a positive charge. Okay? Let's look at, let's go to 136 for right now. Which says, rewrite each of the following using the bond line formula, right? So we've got CH3, CH2, CH2, C double bond O, CH3. Tell me what you know about bond line formulas before we move on.
They're just simple, like lines.
They are lines. What do the lines represent?
Carbons.
The lines represent carbons.
Lines.
The lines represent bonds. What represents the carbons?
The
The vertices, right? Okay. What else do we know about bond line formulas?
Split hydrogen.
Pardon?
You exclude hydrogen.
We exclude hydrogen if and only if what?
Carbon.
carbon. If it's connected to a heteroatom, we have to include it. So if there's hydrogens on nitrogens, you must include them. If there's hydrogens on oxygens, you must include those, right? But on carbon, we assume that any remaining valences in the formula have to be occupied by hydrogen, right?
Right.
Okay. What else do we ignore in bond line formulas for the most part?
Three-dimensional structure.
Okay, we're not gonna, we could draw bond line formulas, and we'll learn more about that in chapter 5, I think, where we're gonna learn about how to give some three-dimensional, but for now, that's not inaccurate. What else? We do take into account some structure, because we zigzag, right? Well, so what are we actually taking into account there? What kind of structure? Kind of the skeletal structure, yeah. So carbon is made up of tetrahedra. And if you ever take a bunch of tetrahedra and you try to connect their corners, it will end up forming a zigzag shape. Okay? So lone pairs, that's right. We assume the lone pairs are there. Sometimes you'll see them put in, sometimes you won't. And you have to know whether or not they should be there or not. Okay? So as I have it right now, I'm not showing the lone pairs on that oxygen, but I know that they're there. And how do I know that they're there?
Because there's not enough charge.
That's right, I'm not showing any charge, right? So I know that it has to be in a state such that the formal charge would be whatever the formal charge is, and right here it's 0, right? So, all right, so how many carbons do I have?
5.
I've got 5 carbons, so how am I going to start with the bond line structure here?
5, okay, to see.
Okay, so we're going to go,
1, 2, 3, 4, 5.
okay? And now what do I do?
You
Put a
put
double
one
bond on the second.
On the second carbon, then we are done, right? So, I've got 1, and that's showing that that carbon is bound to what? One other carbon, so I know that that has to be the CH3 group, right? Because there's got to be 3 hydrogens there to take up the valence. This carbon is bound to 2 other carbons, so that its valences have to be made up by 2 hydrogens. Same for this. This carbon has how many hydrogens?
None.
None, because it has a valence here, here, and here that are all occupied, right? So there are no hydrogens there, and then of course the one on the end is a CH3 as well. Let's look at C. Oop, that's a 3. How am I going to begin?
There's 3 methyls bond to that column.
Okay, so we're going to have this carbon, it's going to have 3 methyls bound to it, right? And it's going to also be bound to a CH2. So I'm going to start off by counting these, 1, 2, 3, 4. So I need 4 carbons. They're going to be in a row. 1, 2, 3, 4, right? This carbon is going to have 3 groups attached to it, 3 other methyls. And what's going to be on the end?
OH.
1, 2, 3, 4. I need to put another bond to OH, right? And that's a common thing that gets people in trouble. They'll go to that end and they'll just write OH, and that really then says that this carbon's bound to OH. So when you put your carbons in, make sure that you're adding the proper amount of bonds that you need for everything. I have to show the hydrogen here. Why do I have to show the hydrogen here?
Bound to oxygen.
Because it's bound to oxygen, but why? No, not why is it bound to oxygen, but why do I still have to show it? What I told you in terms of hydrogens on heteroatoms, that's a rule, but why does that rule exist?
To clarify formal charge.
Exactly, right? So if I was to write this, I wouldn't know immediately whether or not we were talking about an alkoxide, where it was an O minus, or it was an alcohol, right? And both of those can exist. So we show our hydrogens, all of our heteroatoms. Does that make sense? You good? Let's try 137. Draw all the constitutional isomers of C4H8. And I want you all to spend a couple of minutes on a piece of paper working through that. You can work together, you can talk amongst yourselves. Think about all the different ways that we can take 4 carbons and 8 hydrogens and connect them together such that we have no formal charges and everything's good. What do you immediately recognize by that formula, C4H8?
Alkyl.
A double bond? We don't have enough hydrogens, right, to make it
The straight chain.
the complete straight chain where everything's just sigma bonded, right?
Right.
So how many hydrogens would we need if that were the case?
9.
9?
12.
12?
10.
10.
I had to count.
Yeah, that's right. Right, so we're, how many hydrogens shy of that? 2 hydrogens, right? And if we're minus 2 hydrogens, that would be a double bond, right? So there's going to be a double bond in this molecule somewhere. Or does there have to be?
Doesn't have to be.
What could it be?
You can bond carbon. You can have all your carbons double, like single bonded, but bonded together, like in a box like that. Yeah,
Yes.
that's how I did it.
So I noticed that I could make a ring. This is called cyclobutane, right? It's a 4-membered ring. It is minus 2 hydrogens because the 2 ends from this we would have to remove hydrogens from so that those 2 carbons can bond together, right? So C4H8 is said to be unsaturated. It has fewer hydrogens than the number of carbons could actually accommodate, right? For 4 carbons, we can actually accommodate up to 10 hydrogens. But we have less than that, so we call that an unsaturation. Okay, so this is an unsaturated molecule. So this would be one constitutional isomer. How else could we make a constitutional isomer? What would I need to put here? A double bond? Where?
First and second.
Okay, so I can do that. That's one. Is there any other way that I can do it?
Also between first, second, and third.
Any other way that I can do it?
Do it on the end off of them.
Do it
Go
all
between
the
3rd and
same.
4th too.
Do it between 3 and 4? Well, wouldn't that be the same as this?
Correct.
Would be. What else can I do?
You can have a chain of 3 carbons and
With
then
the-
have the double bond come off the second carbon.
chain of 3 carbons. Okay, so there's 3 carbons, now tell me what.
Then double bond off the second carbon
Double bond off the second carbon, what do you mean?
to make another carbon. There.
Like that?
Yeah.
Okay, that works. What else can we do?
You can, I don't know what you call that for this.
Okay. Does that fit? 2, 4, 7, 8. Yep, that works. Anything else we can do? There's one more. That's different as well, right? So if I just give you 4 carbons and 8 hydrogens and ask you to play with them, you can come up with that many different structures. How are those structures related to one another?
They have the same number of atoms.
Okay, so they're all isomers, right? Are they identical compounds? Would you expect them to have the same physical properties? They will not have the same physical properties. They have different physical properties. They have different melting points, boiling points. They give different spectra, which we'll learn about this semester, the whole 9 yards. They are all unique compounds that are comprised of 4 carbons and 8 hydrogens.
Can you clarify what the bottom one is different?
This one? How is that different than this one? You tell me. How do you think that that's different? The connectivity is the same. They do have the same constitution, but are the 3-dimensional shape of that molecule, are they identical? If I think about the double bond as being a plane, think about it like that. What's different about it now? Okay, so this CH3 and this CH3 are on opposite sides of the plane. Where are they here? On the same side.
Is that kind of like a cis and trans?
It is exactly like a cis and trans. Yeah. So we can have cis-trans isomerism. Right? And we can do that when we have rings and we have double bonds because we have restricted rotation. Right? I can't rotate this molecule into that molecule freely. Why? Because the pi bond, right? So if I tried to do that, so if my thumbs were the 2 CH3s and I tried to do, I'd have to break that pi bond to do that, right? So can't do that easily. Should say can't do it. All right, let's look at 139, resonance structures. That arrow right means resonance. What is a resonance structure?
It's whenever there's no one set structure for a compound or whatever it's called. It doesn't just sit in that one thing because it's saying like if you drew both those, you move your bonds around, they're never in since one certain one they go between them.
Well,
Okay.
it's not like actually like they don't exist as one another. They're like a hybrid.
There is a hybrid, yeah. In fact, if you had a microscope and you could look at that molecule, you would only see one molecule.
Yeah.
Okay, it only has one physical structure. Okay, atoms vibrate, so I mean you could take that into account a little bit. But what does it mean?
So when you can create 2 different structures structures by only moving the electrons and not the nuclei.
Okay, I can only move electrons and not the nuclei. So when we think about Lewis structures, Lewis tells us to do what with our electrons? Where do we assign them? We assign them to individual atoms, right? But resonance theory actually helps us correct a defect in that thinking. There's actually a defect in Lewis structures, and that is that electrons, certain electrons, not all electrons, but certain electrons can actually belong to more than one atom in a molecule. That's what a resonance structure really tells us, okay? So if we look at that problem, it shows some arrows being pushed. And what are these arrows telling us? What does that arrow tell me?
Saying that there's two electrons.
Okay, so I'm moving these two electrons, this lone pair, and I'm moving it to where, from where the electrons completely belong to nitrogen to now what? It's going to form a double bond between the nitrogen and the carbon. But I can't exceed the octet rule here, right? And if I do that, I would have 5 bonds to carbon, so I have to move what?
One of the other bonds.
I have to move one of these pi bonds. And now what? Because I can't break the...
Pi bond.
That pi bond is going to move here,
And now,
and then this moves up, right, onto this oxygen. And so when I draw that resonance structure, let's see, we'll have... Right? I think I did that right. That's telling us, right, that this oxygen has a partial negative charge on it, because one of the resonance structures shows a formal negative charge on that oxygen. It also tells us that the nitrogen bears a partial positive charge, because one of the resonance structures bears a positive charge. I have not moved the atoms. I've only moved the electrons, right? What types of electrons am I moving? Okay, they are valence electrons. What else? What kind of electrons are these?
Lone pair.
Those are lone pairs, so I can move lone pairs, and I can move what else?
Bond.
What kind of bonds? Okay, multiple bonds, pi bonds, so they can either be double or triple, okay? What am I not moving? I'm not moving single bonds. When I move that single bond in a resonance structure, if I try to draw a resonance structure, I'd actually move atoms in doing that, okay? And that you can't do, right? So what we notice is that we have a lone pair, single bond, pi bond. Pi bond, single bond, pi bond. You're going to have a pi bond in between to do this movement, okay? It's one of the motifs that you have to have, okay? We'll learn more about that later. But this would be a valid way to draw a resonance structure for this particular molecule. Have I broken any rules? Which one of those would you suppose was the major contributor, the one on the left or the one on the right? That is to say, which one of those individual resonance structures looks most like the hybrid? The one on the left, as you're looking at it? Why?
Charge separation. The charges aren't there.
Okay, so what's bad about charge separation?
Makes it less
unstable.
stable.
Why?
because then you have like stuff in the molecule to split them.
Okay. How many of you have had physics?
I'll take it.
We're in physics.
Okay. Or have you learned anything about charges yet? Probably not.
That's
Okay. But what do you know? I mean, from high school, what do you know about opposite charges? Do they attract or do they repel? They attract, right? So if I take these opposite charges and I stretch them out across the
It's
molecule,
going to be unfavorable.
it's going to be unfavorable because they would much rather be close together, right? So if I take two opposite charges, if I could have a particle that I could hold that was positively charged and a particle that was negatively charged, and I brought them close together, that's how they would want to be, right? And if I tried to separate them, I'd have to put a lot of effort into separating them because they would want to attract one another, right? So charge separation is actually a destabilizing force in resonance structures. You're absolutely right, okay? Now, what would the case be if they were like charges?
It would be more stable.
It would be more stable. You want to get like charges as far apart from one another as possible, okay? But in opposite charges, you want them to be as close to one another as possible. And on the left, we have no charges, right? So, very good. Let's look at 140. And it asks us to supply the arrows. How do we push those electrons to convert the left structure into the right structure? Oops, I'm missing something.
About 6 million? Okay.
I'm missing a nitrogen right there.
That makes sense.
That makes more sense. It matters. How do I go from this structure to this structure? Where do I start with my arrows?
Two lone pairs of electrons and nitrogen.
Okay, I'm going to start at nitrogen with the lone pair. And what kind of arrow am I going to use?
Double.
A double hook, right? Because
Moving two pairs.
we're moving 2 electrons, 1 pair. Okay, now what do I push?
Now you,
Is it
now we have too many bonds on,
the double bond that's there? No, that one now.
Okay, and what do I do with it?
Put it to the bond on the opposite side.
yeah.
Now what do I do?
Now we gotta move the bond off that carbon, it's got to be a bond.
This one?
Yes, sir.
And where do I move it?
Move it
To the right.
next to it.
Now what do I do?
Take the double bond and move it onto the oxygen.
Okay. You will not be great at this in chapter 1, or chapter 2, or chapter 3. But with practice, it will come, I promise.
This is a recurring thing throughout the entire semester.
From now until you finish, get to biochemistry, I mean, this is going to last for you forever. Resonance structures and Lewis structures are very, very important concepts. Okay? Very, very important concepts. What's the molecular formula for this structure? How many carbons, how many nitrogens, how many oxygens, how many hydrogens do we have? Let me erase the arrows just for clarity here. If I asked you that question on an exam, what would you do?
Count the options.
Would learn how to count, right? Yeah, we're going to count. Now typically, in organic chemistry, we label it as CHNO, and then all the other heteroatoms come after, okay? That's typically. So I always start with carbon. How would we identify the number of carbons that we have and keep accurate count?
Count the vertices.
Okay? So I mark them off, right? So I've got 1,
2, 3, 4, 5, 6, 7, 8, 9, 10.
C10. You got a question, Sarah?
Yeah, I have a quick question. Why would we exclude the lone pair electrons and the oxygen on the left structure?
They're there.
But like, why do we not write that and then we write the?
You could.
Okay, so it's not wrong if you write it.
Remember, we can exclude the electron pairs in a Lewis structure. In a bond line structure, you can exclude those. So we got 10 carbons. How many hydrogens do we got?
We got 3, 6, 9, none there. And 1, so it's 10.
Is there one there?
No, there's none there, sorry.
Okay.
Now that makes 10, 11, 12.
Nitrogens?
Is there like, what order those go in your molecular structure?
We typically, I don't care what order you actually put them in, but typically we go C, H, N, oxygen, and then the other heteroatom stays this.
But it's not wrong if you were to mix it up with.
I will not count it wrong. No. But
But
by
that is
kind-
the proper order
Yeah,
technically.
if you look at a molecular formula, it almost always goes C, H, N, O, and then the other heteroatoms. Look at 141 in the book. And I want you all to work together on A through D. Give you a few minutes to work on A through D. We need to draw a resonance structure for that, right? Notice we have a lone pair, single bond, double bond. That's part of the motif that we can have for resonance structures, right? If we push this way, we would break the octet rule.
Right.
Because this is a CH3. That means this carbon would then have 5 bonds. Can't do that. But we can push here and then break the pi bond and put those electrons on the terminal carbon.
Okay.
And in doing so, what happens to our formal charges? What's going to be positive? Oxygen will be positive and the carbon will be
Negative.
negative.
Yeah, it's a low.
It is a lone pair. So which one is the major contributor and which one is the minor contributor to the overall resonance hybrid?
Definitely the first one.
First one. This is the major contributor, so we'll just circle the major contributors, okay? Let's look at B. How can I make a resonance structure?
Could you move the double bond to oxygen,
Which double bond?
the one that it's bonded to?
Okay, so the carbon-oxygen pi bond, I can move.
That up to, and then create another lone pair.
Okay, so why push it that way? Why can't I push it down to the carbon?
Because it already has one last bond, that one oxygen.
It's bonded to
Huh?
it's already bonded to the 3 other things.
Let's look at that. So, that is correct, but if I push the other way, I would say that that is incorrect. Why?
Because the charge is oxygen is more electronegative.
Very good. You always push your electrons to the more electronegative element, right?
Why is it okay in the first one?
Why is it okay in the first one? Why?
Because you do your carbons, you're negative, and then your oxygen's positive.
Well, if I push that way, I would break I can't break the octets. This is the only way that I can
There's an
push.
option. to
That's
do it,
right.
yeah.
I can only have octets, no more. I can actually have less than an octet, right? We've got that here. We know that carbon can have fewer than 8 electrons, but it can't have more, right? And so even though I can do this on paper, makes no sense, okay? Is there any other resonance structure I can draw for this? I can now push this here, right? And I can end up with, let's see, that. Of these three, these are three valid resonance structures. Which one is the major contributor? The original one, right? It is the major contributor because we have no charge separation. But of the two charge separated resonance structures, which one would be the biggest contributor to the resonance hybrid?
The middle one,
The middle one. Why?
the charges are touching.
Well, they're not touching,
Well,
but
they're
they're close.
They aren't-
That's right, they're not as far apart.
stretched out.
All right, very good. You starting to see the pattern in resonance structures? There are a set of rules to resonance structures that we're going to go over, but I never want to start with the rules. The reason is, or at least too many rules, the reason is you all just memorize the rules and don't think about the meaning behind the rules, right? So through exercises like this, we get a sense of why we're doing certain things with the rules and not other things with the rules, okay? So we can move lone pairs, right? And we can move what else? Pi bonds. Can we move sigma bonds in resonance structures? No. We're not going to be able to move sigma bonds, because when we move a sigma bond, we're actually moving an atom with it, and resonance structures tell us that we can't move atoms, right?